Okay. So we were left with this example, if you may remember, to find the Fourier transform of this signal. First we will start, or I'm going to start by saying that, or let's start by evaluating the Fourier transform directly using the formula and see what it comes as the result. So let's find it without thinking of anything else. We can evaluate the Fourier transform if you want to remember the formula, which was this. And when you substitute this signal into the formula, you will see that it has different characteristics for positive and negative t variable. So the boundaries of this integration should better be split into two, like from minus infinity to 0 first. And for this one, we have e to the minus a magnitude t, and the magnitude or the absolute value of t for negative t is minus t, which would make e to the minus a times minus t as e to the at, okay, e to the minus j omega t dt, plus the rest from 0 to infinity. Here, for positive t, the absolute value will be itself. Therefore, e to the minus at will come into the picture. E to the minus j omega t dt. Okay, so these two integrals are things that we need to solve, and the solutions can be achieved by combining the exponents into one term, and since it's a time exponent, its integral is 1 over that thing with boundaries from 0 to minus infinity to 0, or from infinity to 0, and things like that. Just after substitution, of course, we expect this thing to converge, and it does converge for positive a. The first part will converge to 1 over a minus j omega, and the second term will converge to 1 over a plus j omega, or vice versa. I'm not sure which one is the first and which one is the next, but these two terms will come from the integrals, and when you combine them, they are conjugate pairs of each other. Therefore, if you add two conjugate pairs, you're expected to have something real, and that real thing is 2a over a squared plus omega squared. Okay, so this is the direct way of solving the question, and you can do it that way. But in the previous hour, yesterday, I mentioned about one property, and we are still following that property, if you may remember. We are in the topic of properties. This was just an example to illustrate the property that is given here. The even part of x of t, any x of t, will produce the real part of the Fourier transform. And does it have anything to do with it here? This e to the minus at, if you just plot it, you will see that it is like this. Two exponentials decaying at both sides with a decay rate of a. And that is, this is x of t, let's say, is a scaled version of the real part of this thing. Let's call it y of t to be equal to e to the minus at u of t. Okay? And this is x of t is equal to e to the minus a absolute value of t. So what is the relation between each other? What I'm claiming is that x of t is twice the even part of y of t. Because when you take the even part of y of t, it will contain two-tailed version, and if you take the odd part, So the even part will look like x of t, and if you try to just plot the odd part, it's gonna look like this. Oops, of course not looking down to infinity. Something like this. So this is, let's call it z of t, and that is the odd part of y of t. If you see, when you combine the top shape, which is the even part, and the odd part, which is the bottom shape, when you combine them, the left-hand side part, the left side part, will cancel each other. One of them is the positive, the other one is the negative, and they will cancel each other. Only the right-hand side will contribute as twice the right-hand side that we have. That's why I'm telling that the top thing is not really the even part, but it's twice the even part. If you're uncomfortable with by inspection methodology for determining the even and odd parts, there is of course, from calculus, there is of course a mathematical method to determine what is the even part, and that's quite easy. The even part of any signal f of t is equal to f of t plus f of minus t, which is the time flipped around version, over 2. This is the even part. And the odd part, to repeat, of f of t is equal to f of t minus f of minus t over 2. So if you flip around and add this shape like this, and take the half of it, it will be the even part. If you take the other part and make it negative and take half of that, that would be the odd part. That's why this shape, for example, is the odd part. Now, let's come to the original observation. What I'm saying is that the signal in this question, which is x of t, is twice the even part of e to the minus at u of t. Because in the even part there will be a 1 over 2, and this one doesn't have a 1 over 2. Therefore, it's twice the even part. Since x of t is equal to twice the even part of y of t, what we can say is that the Fourier transform of x of t, which is x of j omega, must be twice the real part of y of j omega. You can also find it that way. And this y of j omega is the first, or was the first Fourier transform example that we saw in the beginning of this chapter. It was 1 over a minus j omega, or something like that. What was that? Do you remember the output of that? I'm just not sure about the positive and the negative signs here. So it was 1 over a plus j omega. Okay. So y of j omega was 1 over a plus j omega. And what is the real part of it? And when you multiply it by 2, what is the thing that you will obtain? So you have to determine the real part of this thing. How do you do that? It's a good idea to multiply both the numerator and the denominator with the conjugate, so that they will cancel each other as a multiplication. It will be a multiplication by 1, but the denominator is expected to become real, and only the only complex terms will be appearing in the numerator, and then you will extract the real part from the numerator divided by the denominator real part. So that's the method, and then you just need to multiply it by 2, and it's a good exercise to see whether or not it will be equal to this, and clearly it will be equal to that. Okay, so you can find the answer to this question in this way as well. not necessarily by taking the Fourier transform integral as we did at the top, but also from this methodology by taking the real part. Okay. Now, as you may remember, we were covering the properties, and what was the number of the last property? It was number 3, conjugation and symmetry, in other words. If you take the symmetry in time, then you have to conjugate or take the real part in the Fourier transform. Now we can proceed with the fourth property, which is differentiation and conversely integration, of course. So let's write it: differentiation and integration. Now this is something, or this property comes from the fact of linearity of the Fourier transform. And if you have a linear operator like Fourier transform, then when you apply another linear operator, or if you apply two linear operators to a signal, then you can interchange the places of those operators. You can first apply the first and then apply the second, or you can first apply the second and then the first. So the linear operators can be interchanged in their order. What I'm trying to say is this: if you have x of t with a Fourier transform of x of j omega, which is equal to again the formula e to the minus j omega t dt, what we are going to derive is what is the Fourier transform of this. It's going to be y of j omega, let's say. Let's assume that y of t is the time derivative of x of t. Then its Fourier transform y of j omega will be equal to, from minus infinity to infinity, d by dt x of t e to the minus j omega t dt. Right? And that inside operator can be taken out of the whole expression, and you can also say that we are going to apply the d by dt to the whole Fourier transform. And well, you can think of the expression like this, or, well, it's difficult to see what may come out of this expression, but let's proceed from a different perspective. Okay, in the beginning I thought it may be a good idea to try to take the derivative of the whole expression, but instead of that, let's do it this way. Let's think of the term x of t as an inverse Fourier transform. That would be a better idea. Sorry about that, because the other way of making the proof will be a little bit more complicated. This is easier to see. Let's write x of t in terms of the inverse Fourier transform of x of j omega. It will be much easier to see what's happening here. Okay, let's quit that at the top. Let's proceed from here. X of t is the inverse Fourier transform of x of j omega, in other words. Now, when we take the derivative of x of t, what do I need to do in this expression? I need to take the derivative of the inverse Fourier transform. Okay? And now I can use the linearity of the Fourier transform, which contains an integral, which is a linear operator, and the derivative. And I will push this derivative operator up to the point where it meets a time variable. because t exists only in one place in this formulation. So I'm going to write the Fourier transform integral, inverse Fourier transform integral first, and then I'm going to write j omega, x of j omega, which has nothing to do with t. Therefore, the time derivative will come up to here. And then, finally, the omega. So the derivative that will be applied will be performing upon e to the j omega t. And what is the derivative of e to the j omega t? What is the time derivative of e to the j omega t? J omega times e to the j omega t. So that j omega, let's push here 1 over 2 pi j omega x of j omega, let's write, and then e to the j omega t d omega. Okay. Now from here we can see that this must be the Fourier transform term for our new expression, Fourier, for our new time expression. What is our time expression? It is here. Let's call it y of t. And then, with respect to this expression, we can say that this thing that I write here must be the Fourier transform of that y of t, which is y of j omega. Because it's the inverse Fourier transform of that whole thing, j omega times x of j omega. When you take the inverse Fourier transform, you multiply it by e to the j omega t and integrate from minus infinity to infinity. So that expression is y of j omega, which says that, finally, eventually, it says that the time derivative x of t will have a Fourier transform equal to j omega times x of j omega. This is what is happening. The time signal is time derivative, and the Fourier transform is multiplied by j omega. The same property was valid for the Fourier series. Do you remember that? It was j times k times omega 0 times ak. If you take the time derivative, the Fourier series coefficients will be equal to ak times j times k times omega 0. Times ak. These were the Fourier series coefficients, if you remember. So, is k times omega 0 equal to omega? Yes, it is. Omega 0 was the fundamental frequency, k times omega 0 was the current frequency corresponding to that Fourier series coefficient. So, that is the frequency, k times omega 0. But since the frequencies were discretely separated as integer multiples of omega 0 in Fourier series case, we had k times omega 0. Now the frequencies are not separated discretely. It's not only integer multiples of omega 0, it's just any omega. So instead of k times omega 0, we have omega now in the Fourier transform. And if you think of it that way, the two properties for the Fourier series in differentiation and integration is equivalent to the Fourier transform differentiation and integration formula. So when you take the time derivative of the time signal, you have to multiply the Fourier transform by j omega, as simple as that. Then, of course, we need to think of the inverse operation. What can we say about from minus infinity to t x of tau d tau? What can we think of as the Fourier transform of this expression, the accumulation? Of course, we need to have the inverse operation, right? 1 over j omega. And in fact, that is true. 1 over j omega x of j omega is here. But of course, we have a problem at omega is equal to 0. For the Fourier series case, for the previous case, things were easy. And I said that this formula is valid for all ak except a0. For A0, B0 transformation, just find it separately. For all others, this is the formula. It's safe. But here we cannot say it like that because there is no A0 or anything. There is capital X of J times 0, which is not separate. It's not a discrete entity. It's a continuous function, and that continuous function somewhere exactly at omega is equal to 0, there is a problem. And that problem is solved, it should be solved, and its derivation is a little bit cumbersome. It's not even included in the book. It doesn't show it very rigorously. So I'm going to just write it, which is this. So this accumulation puts an impulse at omega is equal to 0 point. There appears an impulse. If your signal, this is capital X of 0. So if your original signal has no DC coefficient, if the DC of x of t is 0, then capital X of 0 will be 0, and you will have nothing coming from here. So if the DC is 0, then the accumulation will not contribute as an impulse in the center. Okay? But for the others, we may fall into a problem. But this is the formula, anyway. And let's see, okay, let's put the whole thing in a box. We have to check whether the top differential and the bottom integration formulas are inverses of each other. Do we get the same thing? Clearly, if you take the time derivative of from minus infinity to t x of tau d tau, if you do this operation, which is the first fundamental theorem of calculus, this will be equal to x of t. Okay. They are inverses of each other. Therefore, the Fourier transform must correspond to x of j omega. Is it x of j omega? We have to do it like this. J omega times 1 over j omega x of j omega plus pi x0 delta omega. Is this equal to x of j omega? It doesn't seem so. The first term, when you cancel this j omega with this j omega, you will have x of j omega, that it's there. But how about the rest? X of j omega plus, we will have pi j omega x0 delta omega. Now what is this thing? What's the value of it? Any suggestions? It must be 0, by the way, because otherwise it won't be the inverse operation. It will not be exactly the inverse operation. It must be 0 to leave x of j omega only. So the question that we repeat, is this expression equal to 0? Don't worry, the answer is yes. You just need to see why.
It's a constant.
No, it's 0. You only have to say why it is equal to 0. Well, the reason is as follows. As you see, there is an omega times delta omega times a constant. Think of omega times delta omega. Delta omega is valid only at omega is equal to 0, an impulse. At omega is equal to 0, it is non-zero. At omega is equal to 0, what is the value of omega? 0, of course, omega is equal to 0. So, this whole expression at the right hand side is 0 times delta omega. That's why everything is 0. You can think of it like this. You have a what? You have omega function, which is this. right? That's the function of omega, and delta omega is here. If you multiply omega with delta omega will be multiplying the omega function only at omega is equal to 0, and it will cancel. The whole expression will become 0. So we will have x of j omega only, which proves the fact that the derivative and integral formulas are inverses of each other, both in the Fourier domain and in the time domain. In the time domain, it's derivative versus integral. In the Fourier domain, it's j omega versus 1 over j omega like thing. So these are the integral and derivative formulas. The typical question example for the case of using this property is what is the Fourier transform of. The Fourier transform in some cases can be represented like this, a calligraphic sort of f of u of t. What's the Fourier transform of the unit step function? By the way, the unit step function is a little bit problematic because it's not convergent, but it's finite everywhere, so still we can think of a way to overcome the difficulties. If you try to think of it as this integral, let's call it x of j omega. X of j omega is equal to, from 0 to infinity, 1 times e to the minus j omega t dt will be your answer. And so the next question will come into the picture. Can you evaluate this integral? What's it equal to? It's a little bit problematic. When you expand it, you will see that you will encounter a lot of problems in evaluating this thing. So we need, but of course you have to first attack the problem to see its difficulties. Just try to find this integral first, and then you will see problems. You will fall into problems. So we proceed from there and we come up with nothing. So instead we have to think of it this way. U of t is the time accumulation of delta. Or conversely, delta is the time derivative of u of t. Delta t is equal to d by dt of u of t. You can say it like that. They have that kind of a relation. Now, do you remember the Fourier transform of delta t? It was one of the examples that we have seen. It was 1. The Fourier transform of delta t is 1. So what can we say about the Fourier transform of u of t, which is x of j omega, is equal to 1 over j omega times the Fourier transform of impulse, which is 1, plus pi times the Fourier transform of impulse. For the Fourier transform of impulse, the Fourier transform, let's give it a notation. Let's call it f of j omega, something like that. We have to evaluate f of 0 times delta omega. Okay, this was an additional item from the formula. Pi times x of 0 times delta omega is there in box. So that's what we have to insert. It's not only 1 over j omega plus times 1. It's a plus pi times the Fourier transform of impulse at omega is equal to 0 times delta omega. What is the Fourier transform of impulse at 0? What is f0? 1. It's all everywhere 1. So the whole thing will be equal to 1 over j omega plus pi times delta omega. So the Fourier transform of unit step includes quite a divergent thing. 1 over j omega, or 1 over omega is behaving like this, if you remember, 1 over omega. Around omega is equal to 0, it diverges to infinity, which is a problem. So the DC value of unit step should be something like infinity. And it is infinity. And then we have another impulse at the center. So it's difficult to plot it because the first term is imaginary. But if you think of it to be real, let's assume that it's not 1 over j omega, but it's like 1 over omega. Then the shape will be something like 1 over omega for positive and negative frequencies, like this, diverging at omega is equal to 0, plus an extra impulse, something like this. But this plot is not good, okay? I'm not drawing it to be precise. I'm just trying to illustrate the phenomenon here. Because these curves are imaginary, so we cannot plot it on the same axis as the real function. But anyway, this is how it may look like. You can think of it like this. So, as you see, even for the easiest u of t Fourier transform, we need to use some properties. And the property that we use is differentiation and integration property. Very well. The next property, what's the number? This was number 4, I guess. Okay, now we are at number 5, which is time scaling, or time scaling versus frequency scaling. And this property I had already mentioned about it. It was it was inside one of the examples. It simply says that if you squeeze the time signal, you have to expand the frequency Fourier transform signal, and vice versa. In fact, you can solidify the whole concept like this. If you scale your x of t signals time with a by a can be positive or negative. If it is positive, then it would be an expansion, squeezing, and if it is smaller than 1 in magnitude, then it will correspond to an expansion. When you take the Fourier transform of that, you will get this expression. So it is x a times t in the time domain, and it is x omega over a in the Fourier transform. When you multiply time by a, you have to divide omega, the frequency, by a. But since the energy of the whole signal also changes for specifically for finite signals, you have to put a 1 over a in for the whole Fourier transform term as well. The proof is again very simple. You have to just apply the Fourier transform and the inverse Fourier transform formulas, put it inside, make a change of variables, say that t prime is equal to a times t, and you will come up with this new expression as the Fourier transform. It's easy, and it's in the book, I guess, I believe. So we know how it behaves. If you squeeze in time, you have to stretch in frequency. But how about negative A's? This thing, as you see, is also working for negative scalings as well. And the most interesting negative scale that you can think of is -1. That is x of minus t. What is that? It's a time-flipped version of the signal. What is the Fourier transform then? So the example, the typical example, is x of minus t has a Fourier transform equals what? Apply the formula. 1 times capital X of minus j omega, which says that the frequency plot is also flipped around. So if you flip around the time signal, you also have to flip around the Fourier transform on the omega axis, on the frequency axis. Okay. The others, we already had some examples for the other cases. Sixth property is the next property, let's say, which is duality. And again, this property is something that I have previously mentioned in one example. What did I say? We said if you have a rectangular but shape, its Fourier transform is sinc. And if you have a sinc shape as a time signal, then the Fourier transform will be a rectangular shape. That is the duality. Forward and inverse Fourier transforms are duals of each other. And it works like this, to be precise. If you have x of t, which has a Fourier transform of x of j omega, capital X of j omega. Now let's make this capital X of j omega as a shape, which is a function. But let's assume that omega is not omega but time, and say something like this. We have capital X of t. Let's assume that is our time function. Then this new shape, like for example for the rectangle, capital X will be a sinc shape. For the sinc shape, its Fourier transform will be equal to 2 pi times x of j omega, lowercase x of j omega, which is this signal, which was previously in time, but now it's like on the axis of frequency. Alright. Now can we use it in an example? As you may guess, most of the example questions for such properties are fabricated examples. So the question that I will ask is like this. Suppose that you have y of t in the question, which is 2 times sine t capital T1 over t. The question is, what is y of j omega? And from the typical transform pair tables that you have to bring with you in the exam, you will have to make an inspection and notice that if we have an x of t that is a rectangular shape, like it is 1 for magnitude of t is less than t1 and 0 at the outside, the Fourier transform of this thing will be x of j omega is equal to 2 sine omega t1 over omega. So that's in the table already. And notice the similarity between this x of j omega and that y of t. It's only a replacement of omega by t. And therefore, I need to take a look at the inverse Fourier transform of this thing, which was x of t, and I have to multiply it by 2 pi from the property. As you see, it is 2 pi times x of j omega. Or it's not a Fourier transform. What I'm saying is that the Fourier transform y of j omega is equal to 2 pi times the previous x of t, which is x of omega. Of course, you have to write by changing the variable from t to omega. And finally, you say it's 2 pi times 1 if magnitude of omega is less than t1 and 0 else. So it's the same rectangular pulse that we obtain as the Fourier transform of this y of t sinc shape. It's only scaled by 2 pi. Okay? So this is a property in order to solve this awkward problem And again, in order to come up with some property way of solving questions, of course, we have to first observe the plane. So just try to find the Fourier transform of this y of t. Put it inside the integral, multiply it by e to the minus j omega t, and then put a dt and integrate from minus infinity to infinity. Try to find the integral. And I'm sure from calculus, you may guess the difficulties. You have to apply integration by parts and things like that. There's a 1 over t and there's a 2 sine capital T1t multiplying each other. Very problematic. So the better way of solving it is by using the property here. I get it from the property, the duality property. Look at that. The Fourier transform of that capital X is 2 pi times the frequency version of the original factor. There's a 2 pi scale here already. You see that? Well, that can be proven, again, using the formulas. I didn't prove it. I just stated the duality property like this. The proofs are already available in the book and they are not very difficult. The solution of some of the most difficult problems in calculus, like the integrations or the differentiations or the differential equation solutions, sometimes have better and easier ways of attacking the problem using the Fourier theory, including this one. So a good mathematician is also expected to know Fourier theory in order to solve, for the mathematical purposes only, to solve some integrals and some differentials and some differential equations. Another example. Again, I fabricated the example. A nice one. The last one for this hour. We have a new y of t signal that is equal to 2 over 1 plus t squared. And the problem is, what is the Fourier transform of it? Can anybody think of a way to attack the problem again? Using the duality, of course, we are covering that property. In the examination, unfortunately, I will not indicate which property you are expected to use. You have to choose your methodology for this one. For example, for this one, you have to choose duality. Can you see why? Because in the beginning of this hour, we solved an example which was like 2a over a squared plus omega squared. What was the time domain signal for that? That was a Fourier transform. 2a over a squared plus omega squared was a Fourier transform. It was the Fourier transform of our first example this hour. So what was the time signal for that Fourier transform? E to the minus a absolute t. Now, without doing, let's not do any computations, okay? Then, what will be the Fourier transform of this one? Clearly, that a is equal to 1. Because 2a over a squared plus t squared, for a is equal to 1, it will be 2 over 1 plus t squared. So, what is the Fourier transform then? Tell me, without any calculations, just by inspection, tell me what is y of j omega. E to the minus t, it's y of omega. E to the minus absolute value omega, but that's not enough, of course. We have to multiply by 2 pi. Okay. What did I do? I just wrote it. Applied the property. Because I know that e to the minus a times absolute value t would give me 2a over a squared plus omega squared as the Fourier transform. And this guy at the top, y, looks like that Fourier transform. So I'm using the duality property. Did you see what we did here? Okay, is that clear? You understand? All right. So whenever the time domain signals looks like the time domain signal looks like a Fourier transform in your tables of typical pairs, take it from there and apply the duality formula to find the Fourier transform of that. So both sides of the Fourier transform pairs are available for you as the time signals. If the time signal is at the left, the frequency signal is at the right. If the time signal looks like the ones at the right, then apply this formula, the duality property, to find their Fourier transform. We have another. Okay, we have. Excuse me, I said it's the last example, but well, okay. It needs some explanation, so let's stop at this point. After a 15 minutes break, I will continue with the rest of these properties. So let's give a break now.